The hertz is the unit of frequency in the International System of Units and is defined as 1 cycle per second. It is named for Heinrich Rudolf Hertz, the first person to provide conclusive proof of the existence of electromagnetic waves. One of the unit's most common uses is in the description of sine waves and musical tones, particularly those used in radio and other audio-related applications. It is also used to describe the speeds at which computers and other electronics are driven. Definition: the hertz is equivalent to cycles per second. In defining the second, the International Committee for Weights and Measures declared that the standard to be employed is the transition between the hyperfine levels f equals 4, m equals 0 and f equals 3, m equals 0 of the ground state to s1/2 of the cesium-133 atom, unperturbed by external fields, and that the frequency of this transition is assigned the value 9,192,631,770 Hz, thereby effectively defining the hertz and the second, simultaneously. In English, hertz is also used as the plural form. As an SI unit, Hz can be prefixed. Commonly used multiples are kHz, megahertz, GHz and THz. 1 Hz simply means 1 cycle per second, 100 Hz means 100 cycles per second, and so on. The unit may be applied to any periodic event. For example, a clock might be said to tick at 1 Hz, or a human heart might be said to beat at 1.2 Hz. The rate of aperiodic or stochastic events occur is expressed in reciprocal second or inverse second in general, or the specific case of radioactive decay, becquerels. Whereas 1 Hz is 1 cycle per second, 1 becquerel is 1 aperiodic radionuclide event per second. Even though angular velocity, angular frequency and the unit hertz all have the dimension 1 per second, angular velocity and angular frequency are not expressed in hertz, but rather in an appropriate angular unit, such as radians per second. Thus a disk rotating at 60 revolutions per minute is said to be rotating at either 2 pi radian per second or 1 Hz, where the former measures the angular velocity and the latter reflects the number of complete revolutions per second. The conversion between a frequency f measured in Hz and an angular velocity omega measured in radians per second is n. This SI unit is named after Heinrich Hertz. As with every international system of units named for a person, the first letter of its symbol is uppercase. However, when an SI unit is spelled out in English, it should always begin with a lowercase letter, except in a situation where any word in that position would be capitalized, such as at the beginning of a sentence or in material using title case. Note that degrees Celsius conforms to this rule because the D is lowercase, based on the International System of Units. Section 5.2. History. The Hertz is named after the German physicist Heinrich Hertz, who made important scientific contributions to the study of electromagnetism. The name was established by the International Electrotechnical Commission in 1930. It was adopted by the General Conference on Weights and Measures in 1960, replacing the previous name for the unit, cycles per second, along with its related multiples, primarily kilocycles per second and megacycles per second, and occasionally kilomegacycles per second. The term cycles per second was largely replaced by Hertz by the 1970s. Applications. Vibration sound as a traveling longitudinal wave which is an oscillation of pressure. Humans perceive frequency of sound waves as pitch. Each musical note corresponds to a particular frequency which can be measured in hertz. The range of ultrasound, infrasound and other physical vibrations such as molecular and atomic vibrations extends from a few femtos into the terahertz range and beyond. Electromagnetic radiation. Electromagnetic radiation is often described by its frequency, the number of oscillations of the perpendicular electric and magnetic fields per second, expressed in hertz. Radio frequency radiation is usually measured in kilohertz, megahertz, or gigahertz. Light is electromagnetic radiation that is even higher in frequency, and has frequencies in the range of tens to thousands of terahertz. Electromagnetic radiation with frequencies in the low terahertz range is often called terahertz radiation. Even higher frequencies exist, such as that of gamma rays, which can be measured in exahertz. In computers, most central processing units are labeled in terms of their clock rate expressed in megahertz or gigahertz. This number refers to the frequency of the CPU's master clock signal. This signal is a square wave, which is an electrical voltage that switches between low and high values at regular intervals. Hertz has become the primary unit of measurement accepted by the general populace to determine the performance of a CPU, but many experts have criticized this approach, which they claim is an easily manipulable benchmark as some processors use multiple clock periods to perform a single operation, while others can perform multiple operations in a single cycle. For home-based personal computers, CPU clock speeds have ranged from approximately 1 MHz in the late 1970s to up to 6 GHz in IBM power processors. Various computer buses, such as the front-side bus connecting the CPU and North Bridge, also operate at various frequencies in the megahertz range. The speed, or the more correct term bandwidth of networks, including wireless, such as Wi-Fi, 3G, 4G, LTE, etc., is not affected by the myth described above. In general, higher frequency means higher bandwidth or bit rates that lower the times to download big files. In general, however, higher frequencies do not pass through walls, making lower frequencies an advantage, e.g., indoors. Bandwidth is often equated with speed, while latency is the perceived problem that is a distinct measure from bandwidth. While higher bandwidth has an influence on latency, SI multiples, higher frequencies than the International System of Units provides prefixes for, are believed to occur naturally in the frequencies of the quantum mechanical vibrations of high energy, or, equivalently, massive particles, although these are not directly observable and must be inferred from their interactions with other phenomena. For practical reasons, these are typically not expressed in hertz, but in terms of the equivalent quantum energy, which is proportional to the frequency by the factor of Planck's constant.